Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore basic concepts and the first law of thermodynamics, systems, energy transformations, and conservation laws. This session will introduce the fundamental principles of thermodynamics and help us understand how energy behaves in various systems. Over the course of this presentation, we'll cover key ideas such as systems, energy changes, and the core conservation principles that govern thermodynamic processes. Let's get started and dive into these important concepts together. Let's start by defining what we mean by thermodynamic systems. First, we have the isolated system. This is a system where nothing crosses the boundary, no mass, no energy. Think of the universe itself as an example. Nothing enters or leaves. It's completely self-contained. Next, there's the closed system. Here, the mass inside stays fixed, but energy can cross the boundary. A good example is a piston cylinder setup. Heat or work can transfer in or out, but no matter leaves or enters. And finally, we have the open system. This is where both mass and energy can cross the boundary freely. Think of a turbine or a compressor. Air or fluid flows through, bringing energy with it. Understanding these distinctions helps us analyze how energy and mass transfer occur in different systems, which is fundamental to the entire field of thermodynamics. Let's take a closer look at the difference between intensive and extensive properties. Properties that depend on the size or the extent of the system are called extensive properties. For example, total volume, mass, and energy all change when you alter the size of the system. If you increase the system's volume, the total energy or mass will also increase proportionally. These properties are useful when you're interested in the overall quantity of a system. On the other hand, extensive properties are independent of the system's size. They stay the same regardless of how much material you're looking at. For instance, temperature, pressure, and density don't change just because you have more or less of the substance. These are called intensive properties, and they are crucial because they describe the state of the system without depending on its size. Understanding the distinction between these two types of properties helps us analyze and predict how systems behave under different conditions. It's a fundamental concept that ties into the overall theme of thermodynamics, knowing what properties tell us about the system and how they relate to each other. Let's talk about thermodynamic equilibrium. At this stage, the chemical composition of the system remains constant over time. That means no new reactions are occurring, and the types and amounts of substances stay the same. Moving on, the chemical aspect also implies that the pressure at any point within the system doesn't change with time. This stability is crucial for understanding how systems behave when they're in equilibrium. Lastly, thermal equilibrium means the temperature is uniform throughout the entire system. When all these conditions are met, constant chemical makeup, steady pressure, and equal temperature, the system is considered to be in thermodynamic equilibrium. This concept is fundamental because it helps us analyze and predict how systems behave when they're balanced, which ties directly into the overall theme of understanding energy and matter interactions in thermodynamics. Let's talk about processes and cyclic transformations. A cycle is essentially a series of processes that, when completed, bring the system back to its initial state. Think of it as a loop where the starting point and the ending point are the same. Now, the path refers to the actual sequence of states the system passes through during this process. It's like a journey that shows us how the system evolves over time. A process, on the other hand, is any change the system undergoes as it moves from one equilibrium state to another. This could be a physical change, a chemical reaction, or any transformation that shifts the system's state. Understanding these key concepts helps us see how systems behave and transform over time, which is fundamental when analyzing cyclic processes in thermodynamics or other areas. Remember, cycles are important because they often represent real-world systems like engines or refrigerators, where returning to the initial state is crucial for continuous operation. Now, let's talk about work and heat transfer, which are a bit different from properties or state functions. Unlike properties that depend only on the current state of a system, heat and work are what we call path functions. This means their values depend on the specific process or path taken to get from one state to another. When we discuss path functions, it's important to understand the sign conventions we use. Typically, heat input into the system is considered positive, and work done by the system on the surroundings is also positive. Work, denoted as W, is essentially energy transfer that occurs when a force acts over a distance. Think of it as the energy involved when, for example, a piston moves due to a force. Heat, denoted as Q, is energy transfer caused solely by a temperature difference. So whenever there's a temperature gradient, heat flows from the hotter to the colder body. Understanding these concepts is key because they help us analyze energy transfer processes in thermodynamics, and they remind us that the path taken affects the amount of heat and work exchanged, not just the initial and final states. Today, we're diving into the conservation of energy principles in thermal systems, focusing on the first law of thermodynamics. This law essentially states that energy cannot be created or destroyed, only transformed from one form to another. In the context of thermal systems, this means that any heat added to or removed from a system, along with work done on or by the system, must be accounted for as a change in the system's internal energy. It's a fundamental principle that helps us analyze and design efficient energy systems. As we explore these concepts, keep in mind how they connect to the overall goal of understanding energy flow and conservation in engineering applications. This principle is the backbone of energy analysis, ensuring that we consider all energy interactions to achieve optimal system performance. This law essentially confirms why we can trust thermometers as a reliable way to measure temperature. It introduces the idea of the third body. That is, a thermometer acts as a neutral reference point. If two objects are each in thermal equilibrium with this third body, then they are also in thermal equilibrium with each other. This is a fundamental concept because it allows us to compare temperatures indirectly through a common reference. This idea forms the basis of our understanding of temperature measurement. It's what the zeroth law of thermodynamics is all about, establishing a clear, logical foundation for how we define and compare temperature. So, in essence, it confirms that temperature is a consistent property that can be measured reliably using a third body, like a thermometer. This principle is central to the whole framework of thermodynamics and helps us understand how different systems relate to each other thermally. Let's start by talking about the conservation of energy. For a non-cyclic process, the change in a system's internal energy, which we denote as delta U, is determined by the difference between the heat added to the system, Q, and the work done by the system, W in simple terms. If you add heat, the internal energy increases, but if the system does work, it decreases the internal energy. So the relationship is Q minus W equals delta U. Now, when we look at a system undergoing a cycle, the key point is that over the entire cycle, the net heat transfer is equal to the net work transfer. This means that the total heat added to the system throughout the cycle is exactly balanced by the work done by the system, and vice versa. This concept is crucial because it highlights the fundamental principle that energy is conserved. Whether we're analyzing a one-time process or a complete cycle, the energy goes somewhere. It's conserved, and understanding this helps us design more efficient systems. In the context of closed system analysis, this net transfer, whether heat in or out, work in or out, must always balance when considering the entire cycle, emphasizing the core idea that energy cannot be created or destroyed, only transformed. Now let's take a closer look at enthalpy and specific heats. Starting with enthalpy, symbolized as H, which is equal to the internal energy, U plus the pressure, P, times the volume, V essentially, enthalpy represents the total heat content of a system, giving us a good measure of the energy stored in the system that can be used for work or transferred as heat. Next, we have specific heat at constant volume, denoted as CV. This is defined as the partial derivative of internal energy, U, with respect to temperature, T, at constant volume. It tells us how much energy is needed to raise the temperature of a material when the volume doesn't change, which is important in many thermodynamic processes. Similarly, specific heat at constant pressure, Cp, is the partial derivative of enthalpy, H, with respect to temperature, T, but at constant pressure. This indicates how much energy is required to raise the temperature when the system is allowed to expand or contract at constant pressure. Finally, there's an important relation connecting these two specific heats. Cp minus Cv equals the ideal gas constant. This relation is fundamental because it links the heat capacities to the properties of ideal gases, helping us understand how energy transfer varies depending on whether the process occurs at constant volume or constant pressure. Understanding these concepts is key to analyzing various thermodynamic systems and processes, as they form the foundation for calculating heat transfer and work in different scenarios. Let's talk about the idea of a perpetual motion machine. Now, as you might guess, this concept violates the first law of thermodynamics. Essentially, the first law states that energy cannot be created or destroyed, only transferred or converted. So, a machine that runs in a cycle and produces work endlessly without taking in any heat from an external source is impossible. Such a machine would be breaking the fundamental rule that energy must come from somewhere. This is a crucial point because it highlights why perpetual motion machines are considered impossible within our current understanding of physics. It ties back to our overall theme of understanding the laws that govern energy and how they set the limits on what machines can or cannot do. Let's take a closer look at the key variables involved in the steady flow energy equation. Here, H represents enthalpy, which is the energy stored in the fluid due to its pressure and temperature. V stands for velocity, indicating how fast the fluid is moving. Z is the elevation, reflecting the potential energy related to height. Q represents heat transfer per unit mass, and W is work done per unit mass. The steady flow energy equation, or SFEE, essentially states that energy is conserved as fluid flows through a control volume, like a nozzle, turbine, or boiler. It's applicable to open systems where mass crosses the boundary continuously. When we apply this to steady flow systems, we're asserting that the energy entering the control volume, minus the energy leaving, equals the change in stored energy within the system. This helps us analyze and predict how energy transforms within devices and processes. Understanding these variables and the conservation principle is crucial because it allows us to evaluate and optimize thermal systems effectively. It ties directly into our overall goal of improving efficiency and performance in engineering applications. Let's take a moment to acknowledge the sources behind these visuals. First, we have an image from Petrotech.com that shows a detailed cross-section of a turbine, helping us understand its internal structure and how it converts energy. Next, from NASA's website, there's an illustration that depicts thermodynamic principles, which are fundamental to understanding energy systems. Then, there's a diagram from Geeks for Geeks that illustrates various thermodynamic cycles, emphasizing how energy is transferred and transformed in different processes. Finally, from Fiveable, we see a diagram of open, closed, and isolated systems, which is essential for grasping how energy and matter interact within different types of systems. These images collectively highlight the core concepts we've discussed: how turbines operate within thermodynamic cycles, the importance of system boundaries, and the flow of energy and matter. Recognizing these sources not only gives credit, but also shows the diverse perspectives and detailed visuals that support our understanding of energy systems. These visuals are crucial because they make complex ideas more tangible, helping us see how theory translates into real-world applications.